So we have finally made it to Unit 5, which is the foundational piece of inferential statistics. So we start with this very theoretical idea talking about the sampling distributions model. So this is what Chapter 18 is about. Now, of course, we always have our homework. Check the free response question that's posted along with the quiz, with our objective being students calculate values of central tendency and variability from sampling distributions of proportions and means. And then we will go more in depth on sampling or distributions for proportions. And then around chapter 21 and 22, we will then focus on means. So we start off with this kind of idea that comes from calculus. This idea of the central limit theorem for a sample proportion. Now note, we're going to do this interesting little experiment about NFL salaries in class. I'm not going to spoil all too much, but we're going to see something very interesting very quickly. So in the real world, it is very common to sample the population to estimate a proportion of the population demonstrating some characteristic. For example, if I want to figure out all of the lengths of a fish in a given length or in a given lake, the best way to do that is go and actually measure all of the fish. But that's a really tricky thing to do, to actually take a census of the lengths of all of the fishes. How do you know you have them all? And sometimes it's just impossible. So we will rely on sampling to then make an estimate about the true population proportion or population mean. So rather than showing real repeated samples, imagine what would happen if we were to actually draw many samples. So we grab a couple fish the first time, measure, measure, measure. Then we grab a couple fish the second time. They should have different mean lengths. So like we know 9 out of 10 dentists recommend Crest. Were there only 10 dentists that were surveyed? That doesn't make much sense. Or last year, the president's approval rating is currently or was at 38%. Did you think every person in the US was asked what their opinion on the president was? Or how do they know how many people watched the Super Bowl? I mean, the Super Bowl just aired. They estimated 114.4 million people watched. How do they know for sure that that's how many people watched? So if we only take one sample, what makes anyone think that sample is a good representation of the population? Can we trust the results actually reflect the proportion of the population? So suppose you could take many samples of the same size. So maybe we take 10, ask 10 people, and then ask another 10 people, and then ask another 10 people. What would we expect to see if we looked at a distribution of the sample proportions? So we ask 10 people yes or no, yes or no, yes or no. Then we get our population proportion, or the sample proportion, I should say. And then we ask another 10 people, and we get a probably slightly different sample proportion. What we are looking is to graph all of those sample proportions or sample means and see what the distribution looks like. So in other words, we have a distribution of data values that are proportions taken from our many samples, not individual data values. And that is the switch that we're making. We're not just looking at a sample and all of its data, but we're looking at the average from any given sample or many given samples, and then looking at the distribution of averages. So we could then create a histogram of the proportions for many samples. Do you think this histogram might look like the histogram of all possible sample proportions for sample size n? So if you have this idea, or you now have experienced the class experiment that we did, what would the histogram of all the sample proportions look like? So that histogram of all sample proportions is called the sampling distribution of the sample proportions. You know, it's a mouthful. So we can actually compute the expected value of the proportion. And then we can ask, what would this value be for our sampling distribution of sample proportions? And one very nice attribute of sampling proportions, mind you, when I say proportions, we're thinking categorical data, is the fact that the standard deviation of the distribution is an artifact of the actual proportion. So we would expect the histogram of the sample proportions to be centered at the actual true proportion. We call that P in the population. As far as the shape of the histogram goes, we could simulate a bunch of random samples that we did not actually draw. You could do this with a random table or random number generator, as we've done before, by assigning values appropriate to the proportion. It is a really fortunate turn that the histogram will always turn out to be unimodal, symmetric, and centered at P. This is by no random act, but the more samples that we collect, our data will start to look unimodal and symmetric and centered at P. You should think that our data is starting to look like a normal model. So more specifically, it is extremely fortuitous that a normal model is just right for the histogram of sample proportions. So modeling how sample proportions and soon sample means vary from sample to sample is the foundation of the methodologies we use in parametric statistics. If we're looking to study a parameter, what is the true population mean or the true population proportion? That probability that, yes, that people watch the Super Bowl or the chances that people will support candidate X. So the sampling distribution model for how a sample proportion varies from sample to sample provides the ability to quantify variation, how far we are away from the true population proportion, and determine the probability we would observe a sample proportion within a particular interval. So how unusual is our sample that we collected from the true population proportion or mean? So to define a normal model, we need the mean and standard deviation, like normal. For the distribution of the sample proportion, mu, or the mean of the normal distribution, we say is equal to P, the true proportion in the population. Again, this is for categorical data, or our Bernoulli trials that we were conducting. So when working with proportions, knowing the mean, or the proportion, automatically gives us the standard deviation as well. So in our case for standard deviation, we use standard deviation is the square root of PQ over N. That should look familiar. So the distribution of the sample proportions is modeled with the probability model that is our normal centered at our true population proportion, P, with our standard deviation of PQ over N. Remember, and Q is the 1 minus P. So here we go. Here is our graph of the sample proportion. And in fact, the distribution of sample proportions will be centered at the true population mean and going up to the right or to the left, 1 standard deviation or 2 standard deviations or 3 standard deviations. This foundational piece shows us that if we're looking at the true proportion of the people that watch the Super Bowl, we just have to collect enough samples, find those, what people say, yes or no, I watched the Super Bowl, to then find the true population of who did it. It's quite fascinating that this works. And in fact, almost all of our data with enough trials will turn into this normal distribution, however skewed the data actually is. So because we have a normal model, we know that 95% of the normally distributed values are within 2 standard deviations. That's our 68, 95, 99.7% distribution. So we should not be surprised if 95% of the various sampling polls gave results that were near the mean, but varied above or below that by no more than 2 standard deviations. And this is what we mean by sampling error. If you've seen this term, sampling error is not really an error or a mistake. It's not. It's just the variability we would expect to see from one sample to another. So a better phrase for standard error is sampling variability. And when you see that word variability, you should think standard deviation, how far you're away from the mean or the true population proportion. How many people support the president? If we ask enough people, we can find the true mean with a little bit of variability. That's our plus or minus there. So the normal model gets better as a model for distribution of sample proportions as the sample size gets bigger. And like most models, the distribution of sample proportions is useful, which we mean valid, only when specific conditions or specific assumptions are true. So there are two assumptions in the case of a model for the distribution of sample proportions. I keep saying this word. We are talking about categorical data. We are thinking two outcomes or binomial type of distributions. Yes, no situations. So the first one, and this is key, is the independence assumption. The sample values must be independent of each other. It has to be. And the second assumption is the sample size assumption. The sample size, n, must be large enough. And you're like, okay, well, what does that actually mean? So with our assumptions and conditions, and I want to put a star by this right now because this is super important from here on out. We have to check that the assumptions are reasonable by checking the conditions that provide the information about the assumptions. I need you to consistently check these assumptions and conditions. So the corresponding conditions to check before using a normal model to model the distribution of sample proportions are as follows. 1, randomization condition. We are looking for simple random samples. That gives us our independence. We are looking at the 10% condition, which also allows us to verify independence. We are looking for success failure condition, which gives us our adequate sample size. Remember what we talked about last chapter with our probability models. We're looking at NP and NQ being greater than or equal to 10. So let's break those down. With a randomization condition, the sample should be a simple random sample of the population. The 10% condition says the sample size n must be no larger than 10% of the population. If we are less than 10% of our population, we can be justified in saying that it's close enough to be without replacement. As soon as we're greater than 10%, it's going to start changing our probabilities. And lastly, the success failure condition, again, only comes up with categorical data. The sample size has to be big enough so that both NP, the number of successes, and the number of failures, NQ, are at least 10. This condition should look familiar to us. So a proportion is now more than just a computation of a set of data. You collect a sample, you figure out yes, no's, and you get the number. Now, a proportion is now just one example of a random variable quantity. We call those statistics that have a probability distribution. So that point that we were doing all before, one sample at a time, is now one point along our distribution. So 1 point would be our sample proportion. This distribution is called the sampling distribution model for proportions. We make decisions based on what we know about sampling distribution models, but we never actually create them. It would be kind of tough to do this, and as the model requires an infinite number of data values to figure out all of the points along the curve, it's just undoable in the human condition. So we rarely take repeated samples from the sample population and make a histogram, but we can simulate them. We've done that before. But we know that the model would look like, so we never really need to actually create it. So that's kind of our justification for what we do next. So let's be clear about something that we're now discussing. We have a new distribution of values or statistics taken from samples. We're not looking at individual samples, but we're looking at the collection of samples. This new distribution, our model, is to be distinguished from a distribution of individual observations taken from a population. So not just one sample, but all of the samples. And this new distribution currently consists of sample proportions denoted with p hat. Just like we saw y hat was our model before, p hat is our sample proportion. Provided that the sample values are independent and the sample size is sufficiently large, the sampling distribution of p hat is modeled by the normal model with a mean of p, our true population proportion, and a standard deviation of the square root of p times q divided by n. So this is how we justify using a normal model. And you should think, whenever we use a normal model, draw a picture, please. We should see these types of distributions. So suppose we find data that tells us 80% of cars on the interstate exceed the speed limit. Should sound familiar if you live in the state of Michigan. What proportion of the next 50 cars that speed by will be exceeding the speed limit? These are the types of problems we're trying to think of, not just how many of the next 50 cars, but there's going to be a bunch of times that 50 cars drive by. What's the chances that the next 50 cars will be exceeding the speed limit? So we want to find the distribution of the proportion of the next 50 cars that may be speeding on the highway. We are told 80% of all cars, which is the true proportion, on the highway are speeding. Now we have to think about, we first go conditions. Our conditions need to be satisfied. So let's run through them. Randomization condition. The 50 cars can be considered a random sample and thus representative sample for all cars on the highway. 50 cars is certainly less than 10% of all cars on the highway, so we're good with that. And if we do n times p, where the true population is 80%, 50 times 0.8 is 40, 50 times 0.2 is 10. Both are greater than or equal to 10, so we are good. So now we are justified in using our normal model. So we do have to do a couple calculations. The sampling distribution model for the distribution of speeders in 50 cars, we're saying our mean sample proportion, or p hat, is 0.8. This is our true population proportion. Note, that was given to us. Our standard deviation of our sample proportion is the square root of PQ over N. So 0.8 times 0.2 divided by 50 is 0.057. Note, these are all percentages or probabilities of our sample. So our model is our normal model, where we say our mean, P, and our standard deviation, the square root of PQ over N. So the model for our sample proportion always important to know what these terms are. P hat is our normal model with 0.8, 0.057. So the model for our sample proportion gives us the proportion of speeders in 50 cars. So take a look at this. If our true population is centered at our true population proportion, then if we grab 50 cars, what does this first standard deviation mean? Well, 68% of our samples, of our sample proportions, will get these two values. So accordingly, 68% of the samples of 50 cars to have proportions of speeders between 0.743 and 0.857. So we could grab a sample of 50, and we would expect to be within one standard deviation if 75% of those cars were speeding, or up to 85%. 95% of the samples that we collect would have proportions between 68% of those cars speeding and 91% of those cars speeding. And then 99.7% of our samples to have proportions between 0.629 and 0.971. You can see that we're not talking about individual cars. We're talking about selections of 50 cars. And what are the distribution inside those samples of 50? So you might be asking yourself, what about quantitative data? And this is where we're going to put pause on the video, because we first talked about categorical data. We talked about proportions. So proportions summarize categorical variables. That's binomial data. You do exhibit a characteristic or you do not exhibit a characteristic. The normal sampling distribution model is extremely useful in evaluating sample proportion data. But we can do something similar with quantitative data, i.e. means, when we have units of measure. And so, yeah, we can do this. And even better, not only can we use all the same concepts, but almost the same model. And so that's where we're going to pick up in part 2, where we will conclude all of this, do a couple examples, and send you on your way to inferential statistics. See you in the next one, Falcons.